Chemical equilibrium, chapter 13. Chemical equilibrium occurs when the forward rate of a reaction becomes equal to the reverse rate of a reaction. At this point, the concentrations of all the reactants and products remain constant with time. So it does not mean that the reactants are equal to the products. It just means that there becomes a fixed amount of reactants and products. So what we say is that this is macroscopically static, which means what we observe, macroscopically, what we can actually observe, which would be the concentrations or pressures, respectively, for solutions or gases. It's microscopically dynamic, meaning that the reaction is still occurring. We are still creating products, and we are still breaking those products down to create reactants. So the way that we represent equilibrium reactions is by a back and forth arrow. So you can either draw your arrow like this, or the arrows can also be represented in this way, but they mean the same thing. So as I said, we start out, if we're starting with reactants, we notice over time the reactants are decreasing, so we're showing the rate decreasing. Versus once we start forming products, we're going to see that that rate increases. Now, at some point in time, we reach equilibrium, which means that the forward rate and the reverse rate have become constant. They are no longer changing, and they are the same. So here we have the reaction for forming ammonia as a gas. This is the Haber process. So nitrogen plus 3 hydrogens gives us 2 ammonia. We notice, respectively, that the change in concentration of hydrogen initially starts off 3 times as fast as what it is for nitrogen because of this stoichiometric relationship. Recall in chapter 12 when we studied kinetics that we looked at instantaneous rates and how those changed with respect to each other, right? Change in nitrogen over change in time is equal to the change in hydrogen over 3 times the change in time, which equals the change in ammonia over 2 times the change in time. And recall that these are negative, right, which is represented by the negative slope here. And the formation of ammonia is positive because we're forming our product. So here we see we've reached this point in time where we are at equilibrium. So the change in concentration becomes constant. Those rates become constant, and we end up with a fixed amount of hydrogen, ammonia, and nitrogen. Here's a table that shows 3 different experiments starting with initial concentrations that are different. So here we start with our reactants and equal molar concentrations. Once we have reached equilibrium, we have these sets of concentrations, and our equilibrium constant, 6.02 times 10 to the negative 2. Here, if we do not start with reactants, instead we start with 1 molar of products, notice that we end up with a different set of concentrations. However, plugging those into the equilibrium expression gives us the same rate constant. Down here, we start with various amounts of everything, reactants and products. We reach equilibrium. Once again, these are different concentrations because we started out with a different set of initial concentrations. However, plugging these values into our equilibrium expression gets us to the same equilibrium constant. So at any given temperature, you are going to have a specific equilibrium constant. However, you can have an infinite number of possibilities of how you got there in terms of completely different sets of equilibrium concentrations, which are shown here. But whatever you start with, wherever you get to at equilibrium, it has to satisfy this equilibrium constant expression, or I should say it has to satisfy the equilibrium expression such that your equilibrium constant remains the same. So at that specific temperature, if we change the temperature, we will change the equilibrium constant. Your equilibrium expression stays the same. So here is our equilibrium expression as well as our equilibrium constant, Kc. And keep in mind, we don't always have to have the C there. We will see in the next couple chapters, we can have an A, a B, an SP, etc. So our generic reaction here, A plus B, those are our reactants, and their coefficients are J and K. They go on the bottom of our equilibrium expression. So the concentration of A to the power of its coefficient times the concentration of B to the power of its coefficient. And then we put our products on top in the same way, C to the power of L times D to the power of M. So in our equilibrium expression, we are simply looking at our coefficients and making them exponents. And it will always be our products, which is always on the right-hand side of our arrows, over our reactants, which are always on the left-hand side of our arrows. Heterogeneous equilibria versus homogeneous equilibria. So homogeneous means that everything is in the same state. So notice here, we've seen this reaction. Everything here is a gas. Nitrogen gas plus hydrogen gas gives us ammonia as a gas. Here we have the dissociation of the weak acid cyanic acid, or hydrocyanic acid, and that gives us a proton and the cyanide ion. Heterogeneous equilibria means that we have different states of matter represented. Solid, solid, gas, or liquid, gas, gas. So when we have heterogeneous equilibria, we are only going to include the states of matter which are gases or aqueous. We never include solids or liquids. So, as I just stated, the position of heterogeneous equilibria does not depend on the amounts of pure solids or liquids present. We say that these are effectively going to remain constant over time. So we do not include them. So writing an equilibrium expression, we would only have Kc equaling oxygen to the power of 3 due to its coefficient. We do not include potassium chlorate or potassium chloride. So here we have it. K, equilibrium constant, equals O2 cubed. So some highlights that we can look at about our equilibrium expression. If we reverse the reaction, that simply means that reactants become products, products become reactants. And if you look at your K value, you can simply take your K and do 1 over K, and that will give you your equilibrium constant for the reverse reaction. So it's a fraction. So if we look at our balanced equation and we've multiplied through by a certain value, so in the ammonia reaction, we have 1 nitrogen plus 3 hydrogen gives us 2 ammonia. Well, if we have 2 nitrogens plus 6 hydrogens gives us 4 ammonia. We've multiplied everything through by 2, such that then we are going to take our equilibrium constant and raise it to then that power of 2. So n times the stoichiometric coefficients. That's what that means. If you've multiplied through by 2, you're going to take your equilibrium constant and take that to its exponent. Our K values are usually written without units, so this is good because most of us like to leave units off of our numbers anyway. So no units for K. And as stated previously, it depends on the temperature. And when we look at Le Chatelier's principle, we'll see why would these equilibrium constants depend on temperature? Well, it depends on whether or not the reactions are endothermic or exothermic. So changing the temperature can effectively change the amount of products or reactants that we can get. And we're always trying to get as many products as possible for any given reaction. So we can look at changing the temperature. And as we saw in chapter 12 with kinetics, changing the temperature, usually an increase in temperature will speed up a given reaction. And as stated, we see that we have a set of equilibrium concentrations depending upon what our initial set of concentrations were. There are an infinite number of possibilities for our equilibrium concentrations. but at one given temperature, you only have one equilibrium constant. So what is the difference between writing an equilibrium expression for concentrations versus pressure? Nothing, except for we always represent concentrations with brackets. And when we are doing concentrations in this chapter, we are speaking strictly on molarity, not molality or percent composition, anything like that. So Kp is our equilibrium constant with respect to pressure, and here we use parentheses. So we have a specific pressure for these gases that would be given, and we know that pressure is directly related to the number of moles that we have. So this is effectively representing a concentration as well of these particular gases in the mixture. The numeric relationship between Kc and Kp is given by this equation. We're not actually going to focus on this equation, but it is worth mentioning. So whatever your equilibrium constant is in terms of concentration, you would multiply that by RT, keeping in mind that temperature has to be in Kelvin. And you're using your gas constant here, your 0.08206 liters ATMs over moles K. And that is going to be raised to the power of the difference in moles of your products versus your reactants. So total number of moles on the product side minus total number of moles on the reactant side. And that gives you your numeric relationship between K and K. So applications of the equilibrium constant. What is the magnitude of K tell us about a specific reaction? So when our value of K is much larger than 1, and we're talking above 10 to the third, so at least 10,000, K needs to be at least 10,000, that our equilibrium lies mostly to the right, so we effectively see only products at equilibrium. If we have a very small value of K, it means that we have mostly reactants, and this is, we're looking at something that is 10 to the negative 4, so 1/10,000th. Our equilibrium is to the left, and the reaction effectively does not occur. We just have reactants. And if this is what's happening with this particular reaction, then we have to say to ourselves, how do we fix this so that we can actually get the reaction to go? How can we force this reaction to create products? If we have a value of K that is 10 to the negative third all the way up to 10 to the third, then that means that we're somewhere in between, and we have similar amounts of reactants and products at equilibrium. So going along with our magnitude of K, we can look at the reaction quotient, Q. And Q allows us to figure out, with any set of concentrations, how will our reaction shift to get back to equilibrium. So we effectively plug those values into our equilibrium expression, and we solve. We solve for Q. And then we're going to compare Q to K. So when Q equals K, we're at equilibrium and no shift occurs. If Q is larger than K, that means that we have too many products, so we shift to the left in order to create more reactants. If Q is less than K, then we have too many reactants, so we shift to the right to form products. So all of this is really looking at how do we get back to equilibrium. And when we're comparing Q's and K's, this also will tie into Le Chatelier's, because if we're at equilibrium but we add reactant or we add product, how are we going to shift to get back to the balance? Whatever that balance may be, we have to shift to get back to equilibrium. So pictorially, looking at Q is less than K, it means that we have too many reactants, so we shift to the right to get to the place where Q would equal K. We're at equilibrium. Here, Q is way bigger than K, so we have too many products, so we have to create more reactants, shifting to the left to get back to where Q would equal K as well. Solving equilibrium problems. So this is looking at those ICE tables, initial change equilibrium. So we always have to start with a balanced equation for a particular reaction. If we don't have a balanced equation, we would not have the right coefficients, and then we would not have the right equilibrium expression. So once we have our balanced equation, we always write out our equilibrium expression, looking at Kc or Kp. K equals products to their respective exponents divided by reactants to their respective exponents. We would look at the list of our initial concentrations and define then the change that is needed to reach equilibrium, keeping in mind that our change is going to be represented by X. Whatever we're starting with, if we're starting with our reactants, we are subtracting from that side and we are pulling the coefficients down with it. So in the ammonia equation, it's 1 nitrogen plus 3 hydrogen gives 2 ammonia. So our change would be X for nitrogen, 3X for hydrogen, and 2X for ammonia. Once we have our initial and our change, we do the respective math to see what is happening at equilibrium. And then we can plug those values into our equilibrium expression and solve for our unknown. So our unknown could be what is our equilibrium concentration. Our unknown could potentially be K if we have all of our equilibrium concentrations to begin with. So it just depends on what the problem is asking you to do. If you have an initial set of concentrations, then you're going to be finding the equilibrium concentrations, because you also would have to have K. You cannot at the same time find a K value and equilibrium concentrations. That's not going to happen. Now, you can be given equilibrium concentrations, plug those into the expression, and solve for K. So you're either going to be solving for K or solving for equilibrium concentrations. And if you are solving for equilibrium concentrations, the way to check your work is to plug those values back into your equilibrium expression and solving for making sure that they match. So we are going to be practicing lots and lots of ICE tables. And the last bit of this chapter deals with Le Chatelier's principle, which says if a change is imposed on a system at equilibrium, then it's going to shift to reduce that change. Or they also talk about applying a stress to the reaction and then to relieve that stress. How does that happen? The goal is to always be at equilibrium. That is where the reaction settles into because of those rates. So we can look at a couple different things. Concentration, we have two choices. We can either add stuff or we can remove stuff. So anytime we're adding something, if we're going to add a reactant or add a product, we will always shift to the opposite side. If we've added reactant, now we have too much, we can look at that Q versus K and see we have too much reactant, so we're going to shift to the product side, to the right. If we add product, now we have Q is bigger than K, so we have to shift to the left to form reactant. Now removing, if you're removing something, you're shifting to the same side. So as a reaction is progressing, if I'm removing my product, that means then I'm actually going to react more of my reactant to form more of my product. If I remove reactant, then my product is going to react to replace those reactants that were lost in order to get back to equilibrium. So once again, if we add something, we shift to the opposite side of whatever it is we've added. If we remove something, we shift to the same side of where we removed it from. Okay, two situations with temperature. We can look at endothermic reactions and exothermic reaction. Endothermic means that heat is required for this reaction. So it is a reactant. Heat is a reactant in an endothermic reaction. Because heat is required, if we increase the temperature, it means that we are adding heat into the system. Adding something to the reactant side means we shift to the product side because heat is a reactant. So we've added heat by increasing the temperature. We're going to form more products. Conversely, if we are removing heat from the system, we are taking away part of the reactant that we need, so the reaction is going to proceed to the left to the reactant side. So, endothermic reactions, we can think of, it's cold, we want to get warmer. So if we increase the temperature, we can get more products. If we're cold and we're removing more heat, we get colder, so now we're still staying as reactants. Looking at exothermic reactions, we now see that heat is a product. So an increase in temperature means that we're heating up something that already wants to give off heat. This is not a favorable process, so the reaction is going to shift to the left side to form reactants. If we, however, make the reaction cooler, we are allowing more products to be formed because we're effectively then removing some of that heat that is formed in this reaction. So if you're already hot, you don't want to get hotter, hence the shift to the left of reactants. But if you're hot, you want to get cooler, so if we decrease the temperature by removing heat, then we can form more products. Pressure. So changing the pressure only applies to gases. So if you have something that's aqueous in solution, it doesn't matter what the pressure is for that. Pressure only affects gases. It does not affect solids, liquids, or aqueous solutions. I also wanted to say, because I just thought of this, that in terms of concentrations, if we're adding stuff or removing stuff, if we're adding solids or liquids, it does not affect the equilibrium. It only affects equilibrium if we're adding more of our gases or more of our aqueous solutions. So AQs and Gs only, not little L's and little S's. States of matter. Okay, so pressure. So partial pressure of a gas in a particular reaction. This works the same way as changing concentrations. In the ammonia reaction, we've been talking about that a lot in this particular chapter. If we increase hydrogen, it's a reactant, so we shift to the product side. If we increase nitrogen, it's a reactant, we would shift to the product side. If we increased ammonia, which is a product, we would shift to the reactant side. If we add an inert gas, like argon or neon, it's not part of the reaction, it doesn't do anything, so it does not change the equilibrium. If anything, it just gets in the way of the reaction occurring, so maybe we just get to equilibrium slower. Total pressure. So when we're looking at total pressure, this is kind of tied in with volume, right? If we increase the pressure, which is effectively decreasing the volume, we're making the amount of space smaller. We look at number of moles of gas, and we compare the sum of the moles on the reactant side versus the sum of the moles on the product. So total moles reactant versus total moles product. And if we've increased the pressure by decreasing the volume, that means that we are going to shift to the side with fewer moles because it's easier to fit a smaller number of things in a smaller container. So then vice versa, if we decrease the pressure by increasing the volume, now we've got a bigger space and entropy comes into play. So it's much easier to have more things in a bigger space, and it's more favorable. It's a spontaneous process. So these are the ways that we can look at how pressure affects equilibrium. And lastly, although it was not on that slide, catalysts, which are used to speed up reactions, do not actually affect the overall equilibrium. We just get to equilibrium faster. So if we add a catalyst, no shift happens. So here's a slide that is comparing what's happening at different total pressures for the ammonia reaction. It is a function of temperature and total pressure. So here we have 400 degrees Celsius. We've got 48% ammonia, 55% ammonia at 400 atmospheres, and 61% ammonia at 500 atmospheres. As we increase the temperature, we notice that now we only have 13% 17%, and 21% ammonia. So this reaction, if I start off with 48% ammonia at a lower temperature and now I have 13% ammonia at a higher temperature, this tells me that this reaction is exothermic because at the higher temperature I have less products. Also, looking at this, as I increase my pressure, I notice that I'm getting more product, and this is because in that balanced equation, we have 1 mole of hydrogen plus 3 moles of nitrogen, or sorry, that's vice versa. 1 mole of nitrogen plus 3 moles of hydrogen gives us 2 moles of ammonia. So that means I have 4 total moles on my reactant side, 2 total moles on my product side. So under an increase in pressure, meaning I have a smaller space to be in, it's more favorable to have 2 things, 2 molecules of ammonia or 2 moles of ammonia versus 4 total moles on my reactant side. So this table does a really good job of conceptually showing what is happening with Le Chatelier. We can talk about it and talk about these shifts, but here is some experimental data that backs this up that says, how does equilibrium change? How are our concentrations overall changing with respect to temperature and with respect to pressure? And in changing temperature or in changing the total pressure, we can actually change our K values themselves. So what the equilibrium is, we can actually force our equilibrium to exist more on the product side or exist more on the reactant side. So within this chapter, it's important to know what equilibrium is. What does it mean? How do we write an equilibrium expression? What do we include in the equilibrium expression? And how do we use coefficients from our balanced equation? It is important to know what the magnitude of the equilibrium constant tells us about a particular reaction, and then how we can use the reaction quotient Q in comparison to our equilibrium constant K to discuss which way the reaction will shift to get back to equilibrium, which then ties us into Le Chatelier, because if we're adding or removing reactants or products, that's really doing a reaction quotient problem, looking at Q. Q is a specific set of concentrations. How does that relate to K? And then how are we shifting to get back to equilibrium? We also looked at changes in temperature, and we can only look at that if we know whether the reaction is endothermic or exothermic, which means it has to tell us, or it has to list an enthalpy value, a delta H. And in looking at that, exothermic would be a negative energy value, endothermic would be a positive energy value. If we're studying a reaction with gases, we looked at how changing pressures, whether it's partial pressure or total pressure, affects equilibrium. We also looked at how catalysts actually do not affect equilibrium. And then looking at how we can use the equilibrium expression to calculate equilibrium concentrations from initial sets of concentrations and what changes occur. So setting up those ice tables, initial change, equilibrium, and plugging those values into our equilibrium expression. So those are the things to focus on within this chapter, and good luck studying.